Hi there, this is Professor Shannon Gracie. We are working out of Precalculus Enhanced with Graphing Utilities by Sullivan and Sullivan. And today we'll be covering section 5.7, which is about financial models. So we'll be figuring out the future value of a lump sum of money and calculating effective rates of return, determining the present value of a lump sum, and determining the rate of interest or time required to double a lump sum. So let's warm it on up. I don't know if you remember the simple interest formula where interest is applied once and once annually, and you basically have this situation: principal, or the interest rather, is equal to the principal times the rate as a decimal times the time in years. So with this problem, it's asking us, hey, if you borrow 8,000 and after 10 months pay off the loan in the amount of 8,500, what per annum rate of interest was charged? So what are we given here? What was the principal that was borrowed? Good, $8,000. So P is 8,000. What else do we know? We know that we paid it off in 10 months. So 10 months, we have to put that in terms of years, right? So, times 12 months per 1 year, right? So the months would literally divide out. And so so our time will be equivalent to 10/12, which is 5/6. Okay? And then what else do we know? What about interest? Do we know? We know that they paid 8,500, they borrowed 8,000. So do you see that the interest is the 8,500 minus the 8,000, which is 500 bucks. So let's put it all together. So 500 equals 8,000 times R times 5/6. So getting out our calculator, we would have 8,000. Actually, let's just do the whole shebang all at once. So this would be, so 500 divided by 8,000 times 5/6. So I divide both sides by 8,000 times 5/6. Those divide out. Those divide out. So R will be approximately, let's see what we get. Just be careful with your grouping symbols. So let me clear this. We're going to do 500 divided by the quantity 8,000 times 5/6, enter. So R is 0.075, which is 7.5%. And actually, that looks like it was exact, so we'll just say equals. Okay? And actually, R was defined as a decimal, so I don't want to confuse you. Let's just put our conclusion. 7.5% the per, third time's a charm. All right, the per annum rate of interest charged was 7.5%. Okay. All right, so here we go. The simple interest formula officially is if a principal of P dollars is borrowed for a period of T years at a per annum interest rate R expressed as a decimal, the interest I charged is interest equals PERT, principal times rate times time. That's considered to be simple interest. Now, if you consider a payment period, if you do like, so a lot of payment periods are referred to in this section. So let's do this. Let's just make sure you know what they are. Payment periods. And then let's, we'll say type, and we'll say number of times per year. Interest is compounded. Okay, that way I don't have to keep writing the same stuff down. Okay, so we've got some different types. We have annually. And so how many times would that be? Good, once per year. How about semi-annually? Good, that's going to be twice per year. How about quarterly? Great, 4 times per year. And then we get to monthly. And there are, great, 12 months in a year. And daily would be, is considered 365 times per year. All right, so let's take a look at some formulas for compound interest. After T years, the balance A in an account with principal P and annual interest rate R in decimal form is given by these formulas. So if you have N compounding interest periods per year, you'll get A is equal to the principal times 1 plus the rate divided by the number of times interest is compounded raised to the N times T. For continuous compounding, the amount is equal to principal times E raised to the RT. So some other terms. A is referred to as the future value, and P is referred to as the present value. So first example, find the accumulated value of an investment of $5,000 for 10 years at an interest rate of 6.5% if the money is compounded semi-annually, monthly, or continuously. Okay, so what are they looking for? Accumulated value would be good, the future value. So compounded semi-annually. So here we go. The general things we have are the principal P will be the same for each. P is 5,000 and the rate is the same. So the rate as a decimal is 0.065. and the time is equal to 10. For part A and B, we're going to be using this formula here because there are a finite number of compounding periods. So for this guy, do you see that n will equal 2, and for this one, n will equal, good, 12. So here we go. A equals, so the future value will equal to the principal, 5,000 times 1 plus 0.065, our rate, divided by n, which is 2, and then raised to the nt, so 2 times 10. So let's break out the graphing calculator and figure this out. So we'll have 5,000 times parentheses 1 plus 0.065 divided by 2, and 2 times 10 is 20, so we'll raise it to the 20th. Okay, so at this amount of interest, at 6.5% interest, if you have 2 compounding periods per year, then your investment will get to be $9,479.19 approximately. So I'll put this here so you know how I entered in this stuff here. And we'll put our result. Okay, so A is approximately $9,479.19. That is the future value of the account. All right, so compounded monthly. What changes? Good, the n changes. So we'll have 1 plus 0.065 divided by 12 now, and then raised to the 12 times 10. So, grabbing our computer, we'll have, I'll clear this one, so 5,000 times 1 plus 0.065 divided by 12 raised to the 12 times 10 is, good, 120. And for this one, we get a little bit more money. You see that? And it makes more sense, right? Interest is applied more often, so you'll get more money. Okay, so here we go. A is approximately $9,560.92. All right, and now we go into, so this formula was used for these two here. So we've got, these two follow this formula. But when you're compounding continuously, we're going to use A equals P times e to the RT. And so we get A equals 5,000 times e raised to the 0.065 times 10. So let's see what we get. And 0.065 times 10 is what? 0.65. And look at that, even more money. All right, so A is approximately $9,577.70. All right. So if you're looking, at a bank account, right, you're going to want to have have a higher rate of interest. But if you're looking at something like a credit card, you'd want for yourself a lower rate of interest. So the next bit of material is called effective rate of interest. So the effective rate of interest and it's denoted R sub E of an investment. So this is of an investment earning an annual interest rate R is given by if you've got a finite amount of times you're compounding, then you do this. You get RE is equal to 1 plus R over N raised to the N minus 1. If you are doing continuous compounding, you'll have the effective rate of interest will be E raised to the R minus 1. Okay, so let's take a look at these guys. This one is finding the present value. Like if you know how much money that you want to get from an investment, then and you need to, and you want to know how long it needs to stay in, this will give you the answer. So this actually still is going to use those other formulas. So we have, let's identify what we have. To get 800 after 3.5 years. So do you see that A is 800 and then R is 0.07 and T is 3.5 and then what else do we have? We're looking for the principal, the present value, and this one will be N is 12. And again, we're using A equals P times 1 plus R over N raised to the NT. So let's do it. 800 N for A, P stays as it is, and then we'll have 1 plus 0.07 divided by 12 raised to the 12 times 3.5. So if we isolate the P by dividing by all that, do you guys see that P will be equal to 800 divided by all that other stuff? So 1 plus 0.07 divided by 12 raised to the 12 times 3.5. And that's what we'll put into the calculator. So let's see what we get. So we have 800 divided by 1 plus 0.07 divided by 12. I'll end the parentheses. And that's raised to the, I'm going to just do the product in parentheses. That'll be raised to the 12 times 3.5. You know, I'm probably being overly careful, but I want to make sure that the whole denominator is in parentheses. I'm sure it's fine, but better safe than sorry, right? Okay, so we would need to put in, let's just round up to the nearest dollar. So we need to put in a principal of approximately $627. And this is how everything was entered in. Okay, so, all right, let's see the difference between the monthly compounding versus continuous compounding. So this one, we're going to use the same information. P is equal to, or not P, my bad. A is equal to P times E raised to the RT. And again, A is 800. R is 0.07. T is 3.5. And then we don't need N. We're all set. We have everything we need. So here we go. 800 equals P times E raised to the 0.07 times 3.5. And do you guys see that if you divide both sides by all that, we'll have P is equal to 800 divided by E raised to the 0.07 times 3.5. Let's see what we get. Okay, so again, well, $1 less. You could round down to 626. And so maybe we should have done, you know, so we could get a better comparison. Let's go ahead and go to the nearest cent. So that would have been $626.61. This guy is going to be, oh, that's the last one. Let's copy this. All right. And this one would be just a little bit less. So P would be approximately $626.16. Okay. Moving right along, here's a couple of examples for the effective rate of interest. So this is compounded quarterly. So the general formula is effective rate of interest is going to be 1 plus R over N raised to the N minus 1. And let's identify what everything is. So in this case, we just need R and N. So R is equal to, good, 0.05, and compounding quarterly, N is 4. So let's do it. The effective rate of interest will be 1 plus 0.05 divided by 4 raised to the 4th minus 1. Okay. So what you're going to see is it's a little higher, right? So effective rate of interest ends up being a little bit more than the stated. This happens, when you buy a house, they say a certain amount, but the actual interest rate sometimes is a bit different than what it seems. So the effective rate of interest is approximately 0.0509 will do, which is 5.09%. Okay. Now let's take a look at what happens when you're doing continuous compounding. So the formula changes to the effective rate of interest is e to the r minus 1. And we know that r is 0.05. So we'll get e to the 0.05 minus 1. And that minus 1 is not in the exponent. Make sure you end these parentheses and then do your minus 1. All right, so let's take a look. Do you see this is going to be a little higher because interest is compounded more often. So we've got this going on over here, how we entered it in. And so this will be approximately, actually, 1.3, which will give us an effective rate of interest of 5.13%. Okay, so the next example is determine the rate that represents the better deal. And let's say the better deal for an investment, just to make sure, because it always depends on whose perspective, right? Okay, so 9% compounded quarterly or 8.8% compounded daily. All right, so let's check it out. So to do this one, what would we look at? Good. We'd want to look at the effective rate of interest for each. And in this case, since it's for an investment, we'd want a higher effective rate of interest. So the effective rate of interest for the first one is going to be, so R equals 0.09 and N equals 4. So this would be 1 plus R over N raised to the N minus 1. So RE, effective rate of interest, will be 1 plus 0.09 divided by 4 raised to the 4th minus 1. And that is oh, it's raised to the 4th. I'll change that on the page. Okay. So that's going to be this is what we get when we do this one. Okay, and this was supposed to be a 4. Okay, so the effective rate of interest is approximately 0.0931, which is 9.31%. Now, looking at the second case, the compounded daily, the R will be 0.088 and N will be, good, 365. So, the effective rate of interest will be, it's the same formula, just different, a different rate and different number of times you're compounding. So let's see what it is. Oh, and this is raised to the 365. I forgot my power. And let's see what we get. Okay, so for this one, and again I have to put in the power here. So we get approximately 1.092, it looks like. Is that right? 1.092. Yes. So that would be, oh, you know what? I didn't do the -1. I was like, that's really high. All right, so let me go back and do the -1. Okay, let's do it. I'm just going to go second entry, and then we'll do -1 at the end. There we go. Now that looks better. So 0.0920 it looks like. What did I round to last time? 4. So 0.0920, which gives us an effective rate of interest of 9.2%. So since this is an investment, the first one is going to be better because it has a higher effective rate of interest. Okay? So let's write that down. 9% compounded quarterly. Is the better deal. Since the effective rate of interest is higher. Okay? All right. So here we go. Here's a kind of a good application. I was thinking of the second one, but they're both good. All right. How many years will it take for an initial investment of $25,000 to grow to $80,000? And we're assuming a rate of interest of 7% compounded continuously. So when you see that word continuously, you should automatically recognize that we're going to have A equals P times e to the RT. And what do we know? What is the principal? Good, 25,000. And what is A? Awesome, 80,000. And we also know R is 0.07. Very good. Now, by the way, if you wanted to know like doubling time for your money, this is how you would do it. But instead of putting 80,000, you'd double your principal. So you would have put 50,000 to find the doubling time. Okay, so we'll just go on with this one. So A equals PE to the RT. We'll have 80,000 equals 25,000 e to the 0.07 times t. We are trying to find t. So here we go. If we divide both sides by 25,000 so we can isolate the exponential, then we'll have 80 25ths reduces to what? I think 16 fifths, something like that, is equal to e to the 0.07t. And then what do we do to both sides? Awesome. You natural log both sides because you're okay, so then we will have natural log of 16 fifths is equal to, good, 0.07 times t. So then, dividing by 0.07 on both sides, I'll show that work. We will have natural log at 16 fifths divided by 0.07 is t. So let's see what we get. Be careful on this one. After you do the divided by 5, end the parentheses, and then do your divided by 0.07. Let's see how long it'll take. Okay, it'll take about 16.6 years. So t is approximately 16.6 years. So if you had 25 grand and you could find something that paid 7% interest and you just left it alone for 16.6 years, it would grow to 80,000. So an account with a present value of 25,000 at a rate of 7% compounded continuously has a future value of $80,000 after 16.6 years. Okay? All right, so then this next one, Colleen and Bill have just purchased a home for $650,000, with the seller holding a second mortgage of $100 grand. They promised to pay the seller $100,000 plus all accrued interest 5 years from now. The seller offers them 3 interest options on the second mortgage. At 12% per annum, they could do simple interest, 11.5% interest if it was compounded monthly, and 11.25% interest compounded continuously. So what option is best for Colleen and Bill? So Colleen and Bill are going to want to pay, good, they're going to want to pay the least, right? So let's see what they would pay with the different plans. So for Plan A, simple interest, remember, is principal times rate times time. Okay, so the interest they would pay would be 100,000 times their rate was 12%, so that would be 0.12, and then they would be doing that for 5 years. So the interest they would pay is 100,000 times 0.12 times 5. So they would pay $60,000 in interest. So what that means, they would end up paying what? So the amount paid would be principal plus interest. So their amount would be 100,000 plus 60,000. And so if they did 12% simple interest, they would have to pay the sellers $160,000 at the end of the time. All right, so part B says what? 11.5% interest compounded monthly. So 1 plus R over N raised to the NT. So, oh, and our P is in here. So 100,000 times 1 plus, that's going to be 11.5% will be 0.115. And it's compounded monthly, so divided by 12, and then raised to the 12 times 5. So if we put this guy in the calculator, son's got the TV on loud, sorry. And 12 times 5 is 60. I'll just do that. Oops, we got to raise it to the 60. Uh-oh. There we go. So this deal is not going to be as good for them. Do you see that? Because they would be paying, they'd be paying more, they'd be paying quite a bit more. So for this one, the amount they'd pay would be approximately $177,000 and or $177,227. So now let's look at part C, where it's 11.25% interest compounded continuously. So this one would be A equals P times E raised to the RT. So A equals 100,000 times E raised to the 11.25 is 11.25, so we'd have 0.1125 times 5. So let's see what this one is. Okay, and this one a little less than option B, but more than option A. So the winner is simple interest at the highest rate of interest. The simple interest won. Okay, so this amount was approximately $175,505. So part A wins. So the option A is best. For Colleen and Bill. Okay, so that wraps it up for today. Have a fabulous day, and I will talk to you soon. Bye.